Hey all, let's take a look at your test one review here. So your first problem is going to be a difference quotient problem where I'm asking you to simplify the expression f of x plus h minus f of x over h. Now, of course, your test will look identical to this. The difference quotient will be given, and then you'll be given a function to plug into it. In this case, I'm plugging in the function x over x minus 7. So in this problem, my f of x plus h minus f of x over h, f of x plus h, all I do is I replace the x with an f of x with an x plus h, so I get x plus h over x plus h minus 7. That x plus h took the place of that x. Minus f of x, which that's just plugging our function in there, all divided by h. Now I need to simplify that expression. You know that in order to simplify a fraction, you can't have any fractions within the fraction. So I knew I needed to multiply by both of these denominators here. That's what I've done. So I multiplied by the denominator x plus h minus 7 and x minus 7. I have to multiply both the numerator and denominator by those terms in order to multiply by an understood 1. Now, when I multiply by those terms in the denominator, all of those terms are just multiplied together. That's where this came from. H times x plus h minus 7 times x minus 7. I knew I needed to simplify my numerator, so when I multiplied, I distributed these terms into each one of these. When I distributed it into the first term there, the x plus h minus 7 canceled with this x plus h minus 7, leaving me x plus h times x minus 7 over here. Now for the second term, I had minus x, and then this x minus 7 would cancel with this x minus 7, leaving me minus x times the remaining trinomial term, x plus h minus 7. After that, all I did is I multiplied out in my numerator. I had x times x is x squared. Then I had minus 7x plus hx minus 7h. That's where this group came from. I subtracted that by, I distributed an x into this group. So minus x squared plus hx minus 7x. And then all over my same denominator. Please don't forget that that denominator is carried over. We don't want to distribute or anything, but we have to leave it down there. Now, my goal in this problem is to cancel out an h. You'll be able to get to that goal if you simplify the terms in the numerator. You'll always have terms that cancel out. Notice x squared minus x squared, hx minus hx, minus 7x minus a negative 7x. All of those cancel. So the only term I had left with minus 7h here. Now, I knew I needed to factor out an h. I went ahead and did that. I said, well, if I factor an h out of that, I'll have a minus 7 or a negative 7 left over. Then that h in the numerator can cancel with a factor of h in the denominator, leaving me the final answer, negative 7 over x plus h minus 7 times x minus 7. That would be the final excellent answer there. Now, I move on to the next one here. Just an exponential equation. So I'll give you something like 5 raised to the 2x plus 1 power is equal to 37. We're supposed to find the exact answer and the decimal approximation to 3 decimal places. So in order to solve an exponential equation, I want you to remember you have to take the log of whatever that exponential base is of both sides. Log functions are the inverse of exponential functions. So I take the log base 5 of the left, I take the log base 5 of the right-hand side. Now, log base 5 exponential base 5 by definition cancels out. That's why you have the 2x plus 1 on the left-hand side. By the property of logarithms, I can say log base 5 of 37 is equal to the natural log of 37 divided by the natural log of 5. So I can say that's how I rewrite. If you have a calculator that can't handle the log of a different base, of course, if you have an 84 calculator, you can do this on the calculator, and this step is not necessary. This step is necessary if you have a basic scientific calculator, though, and it's just a good thing to do anyway. So I prefer to rewrite as the natural log of 37 over the natural log of 5, even if my calculator is capable of computing the step earlier. Now, at this point, I want the exact answer. So I need to solve for x, and I need to leave this as is. Do not get a decimal for this expression right now. So I subtract 1 on each side, and then in order to solve for x, I would then divide that expression by 2. That's what I have right here. This would be the exact answer. Now I can say, well, the decimal approximation. All I did was I entered this expression into my calculator, and I got to that decimal approximation of 0.622. And I do want both of those answers there. For number 3, we have the cosine of the inverse cosecant of x over 5. And you're supposed to rewrite this as an algebraic expression. The key to doing this and any problem like it is to remember that any inverse function is always just an angle. So you can call it an angle. Let's let that inverse cosecant of x over 5 be theta. And then I can say, well, what do I know about theta? Well, I can take the cosecant of both sides and say that the cosecant of theta would then equal x over 5. That gives me information to be able to draw a trig triangle with respect to theta. So I can say, oh, well, I know cosecant is the reciprocal of sine. The mnemonic you're supposed to remember for your right trig triangle sides is SOHCAHTOA. Sine is the ratio of opposite over hypotenuse. Since secant is the reciprocal of sine, then it's the ratio of hypotenuse over the opposite within a right triangle. So at that point, I drew my right triangle and I said, okay, here's my angle theta. I know that the hypotenuse of this triangle has to be x. That's where that came from. And then I knew that the opposite side had to be 5. So I took my hypotenuse over opposite. And then my remaining leg, what I want you to remember is that any leg is always the square root of the hypotenuse squared minus the other side squared. That will always work, and in this case, it gave me the square root of x squared minus 25. Once you get your right trig triangle defined, this problem is so easy because the whole point of doing all of this was to be able to rewrite the original expression. We've allowed theta to represent that inverse cosecant function. So your answer is just, well, what is the cosine of theta? And in order to know that, you look at your right trig triangle here, and you say, well, cosine of theta would be the ratio of adjacent over hypotenuse, and that's going to be the square root of x squared minus 25 over x, which is your final answer up here, and you get to that. Up next, for number 4. If I tell you something like the secant of theta is 37 over 12, and I tell you that theta is an angle in quadrant 4, it's greater than 3 pi over 2, but less than 2 pi. So in order to kind of show my thinking on this, I went ahead and drew a circle. Note it's not a unit circle because I have a radial length of 37 on here. So when I drew my triangle, my angle theta always has to be connected to the x-axis. This would be my right angle right here. So the distance from the origin to any point on the circle is always going to be the hypotenuse of the triangle that I draw. So I can say, well, okay, I know that the secant of theta is 37 over 12. I was thinking, well, I know that that's the reciprocal of cosine. Cosine would be adjacent over hypotenuse. So this is hypotenuse over adjacent. So I said, well, this means that this is my hypotenuse, and then that this is my adjacent side. So I went ahead and labeled this side 12, this side 37. Once I know that, then I can find the remaining side of my triangle. What I do have to keep in mind here is that the vertical component in quadrant 4 must be negative. It's moving downward. So I use my Pythagorean theorem here, and I called this side of the triangle B. 12 squared plus b squared is 37 squared. 37 squared minus 12 squared gave me 1225. So in general, b would equal the positive or negative square root of 1225. That could give me a minus 35 or a plus 35 up here. Well, we know it's not plus. It's moving downwards. The y component is negative. That's why I had to choose the negative 35 down there. But now that I have my triangle defined, I go in and I find all of my trig functions. The sine of angle theta, this is your, again, SOHCAHTOA. So I can say sine is the ratio of opposite over hypotenuse, negative 35 over 37. Cosine, we would know just from adjacent over hypotenuse, or we also know it's the reciprocal of what was given, 12 over 37. The tangent is the ratio of opposite over adjacent. Well, the ratio of opposite over adjacent is going to be negative 35 over 12 there. Once you get these, then the reciprocal identities are easy. Once we know that the sine is negative 35 over 37, we know that the cosecant is the reciprocal of that, 37 over negative 35, or as you'll see, I always prefer to keep the negative in the numerator. Doesn't matter though. The reciprocal of cosine, secant, which of course was also given, and then the reciprocal of tangent would give us negative 12 over 35 there. For the next problem, this is the one where I'm wanting you to be able to make conjecture or understand what an instantaneous velocity is at some instant in time, given an average rate of change over an increasingly smaller and smaller interval. We should always see our average velocity start to approach some value as they get as the time gets less and less and less. Notice in this case, first time elapsed was 1 second, then 1/10 of a second, then 100th of a second, then 1,000th of a second. Over these time intervals, we should see a pattern in what our average velocities approach, and sure enough, that's what happened in this one. So in all of these problems, all you're doing is finding the average rate of change from the first time given to the second time given. So you'll see what I did here is I just said, well, this is going to be the position function measured at 3. So this is s of 3 minus s of 2. I plugged a 3 into this function, I got a 135. I plugged a 2 into it and got a 110. Divide that over the change in time, 3 minus 2. Now, my numerator had a difference of 25 units. My denominator had a difference of the 1 second. So this was an overall average rate of change between 2 and 3 of 25. Now, I didn't specifically give units because I didn't want to concentrate on that in this problem. And I also tried to keep the problem exactly as it was in the homework, and they didn't have any units. So I can't say whether this is 25 feet per second or meters per second or miles per hour. I don't know. So I'm trying to keep it exactly like the homework so we don't need to put any units on our final answers here. Average velocity we'll just say is 25. And then the average rate of change between 2 and 2.1. In this problem, all I did was I plugged 2.1 into the position function. So that's plugging it into this right here. I got the 113.4. As we've already determined, the position at 2 is still 110. Notice your second term that you're subtracting is always going to be 110 because you're always subtracting s of 2. My change in the numerator was 3.4 units over the change in the denominator of 0.1. That gave me an average rate of change of 34. Now, there is a pattern here. I know that this went up plus 9. Notice this one's going to go up plus 0.9. The one after that is going to go up 0.99. So, 0.09, I should have said. And then the one after that would go up 0.009. So if I said, hey, I want you to find the average rate of change between 2 and 2.0001, I promise you, it would be 34.99999. What about the one after that? 34.99999. What number are these average velocities approaching? Well, it's approaching a number of 35. Okay, up next, this is the problem where I'm having you look at a graph and answer questions about functions, functional notation and limits given that graph. So in this one, it starts off f of 3. Well, f of 3, the function's value at 3 up here is defined to be 4. That's where that came from. The limit as x approaches 3 from the left. And I said, well, the limit as x approaches 3 from the left, it's going to be coming in and saying, well, as I'm approaching 3 on the left-hand side, it's going to this y value. That y value is 3. The limit as x approaches 3 on the right-hand side, it would be coming down as I'm approaching 3 on the right. It's still going to that same y value of 3. That's why these answers are the same. And since those answers are the same, since the limit from the left is the same as the limit from the right, then the overall limit as x approaches 3 is also 3. That's the only time the overall limit exists, when the left and right-hand limit give the same value. Now, f of 5. F of 5 in this problem, you'd say, well, the function evaluated at 5, that's yet another answer of 3. A lot of answers of 3 here. Up next, the limit as x approaches 5 on the left-hand side. As I approach 5 on the left-hand side, I need you to understand you're on this part of the function up here. And as you get closer and closer and closer to 5 on the left-hand side, your y value is just getting ever and ever closer to 7. As you're approaching 5 on the right-hand side, you're on this part of the function, and the closer you get to 5 on the right, the closer the y value is getting to 2. Since the limit from the left does not equal the limit from the right, that's the reason the overall limit as x approaches 5 does not exist. Now, part I, it's saying, well, what's the function evaluated at 4? Notice at 4, there's no solid dot or anything like that. That's not a problem. If I ask you what f of 4 is, then you just say, well, f of 4 is right here. The line is solid through there. It's just you don't need a specific point there to define it because you got the whole line. Well, what is the y value there? The y value there is a value of 5. That's where that came from. Now, whether I'm approaching 4 on the left-hand side or 4 on the right-hand side, it's going to that exact same value of 4, which is why the limit as x approaches 4 from the left and right are both 5, and the overall limit as x approaches 4 is 5. It's a continuous function at 4. Now, I love this next problem. I ask you to sketch a graph of a function that satisfies all the following criteria. So as we do this, I'll go ahead and show the part of the graph that satisfies this. Now keep in mind, in order to graph a function, it's going to need to pass the vertical line test too. So please notice, nowhere in this graph would I ever have two y values for one x value. It passes the vertical line test. It is definitely a function. Now, on the function that I have drawn, I had to show that as x goes to negative infinity, the y value goes to infinity. Well, that's what I've done right here. Now, did I have to show it going up parabolically like that? I didn't. I could have just drawn a linear function there and done that. That would have been fine. But however you do it, you have to show as x moves to the left, the y value is moving upwards. The second component, the limit as x approaches negative 2 is negative 5. So that tells me, since it's an overall limit, that means as I approach 2 from the left or the right, the y value better go to negative 5. That's precisely what I tried to do right here. As I approach x equals negative 2 from the left, the y value goes to negative 5. As I approach negative 2 from the right, the y value goes to negative 5. Now notice, I drew an open circle at 2. It didn't say whether the function was defined at negative 2 or not. You could have drawn a solid dot, open circle, does not matter. I could have defined f of 2 up here. It still wouldn't matter because the limit as x approaches negative 2 is negative 5, regardless of whether I have open circle, solid dot there, or a solid dot up here. So this would have not changed a thing as far as the limit as x approaches -2. So now we have both of these two satisfied, and I would have had this part of the graph right through here drawn. And then I had to say, well, okay, be careful moving on up through here. I needed to show as x approaches +3 on the left-hand side that the y value goes to infinity. Well, anytime you want to show that the y value goes to infinity at a finite x value, you have to draw a vertical asymptote. That's what I did. So I said vertical asymptote at x equals 3 here. And then at that vertical asymptote, as I approach it on the left-hand side, I needed to show that the y value goes to positive infinity. That's where I drew this part in right here. Did it have to be drawn exactly like that? Nah, but pretty much. I could have made it maybe do something like this, and it still would have been fine. That still satisfies the criteria. The limit as x approaches 2 on the right, it's still going to -5. The limit as x approaches 3 on the left, still going to infinity. So that would have been okay. I drew a more simplistic graph than that. The limit as x approaches 3 on the right has to go to -infinity. So I knew as I'm approaching 3 on the right-hand side, my y value would be going downward. But before I really drew in this part of the graph, I had to think about, well, what's happening as x moves further to the right? As x moves forever to the right, the y value has to approach 2. This is a horizontal asymptote. Now, this function only has a horizontal asymptote for the positive x values. For the negative x values, it goes to infinity. But as x approaches positive infinity, I had to show y goes to 2. Just as I need to draw in vertical asymptotes, I needed to draw in the horizontal asymptote to show, hey, this is the line y equals 2. And as x gets large, it's going to approach that line of y equals 2. But as x approaches 3 on the right-hand side, the y value has to go off towards -infinity. Had to satisfy both of those criteria. Next problem. Both of the next two problems are algebraic solutions to limits. So if I give you something like the limit as x approaches 100 of x minus 100 over the square root of x minus 100, we know we can't just simply plug in a 100 because your numerator would be equal to 0 and your denominator would be equal to 0. These are the types of problems where you're supposed to remember there's going to be something that cancels out if this limit exists. So what I did is I used difference of two squares in the numerator. I said we know x times or square root of x times square root of x is x. 10 times 10 is 100. So that factored to be x, the square root of x plus 10 times the square root of x minus 10. Please, please, please remember, you must keep that limit notation until you physically plug a 100 in for x. So I have the limit as x approaches 100 of the square root of x plus 10 times the square root of x minus 10 over the square root of x minus 10. At that point, the square root of x minus 10s would cancel out, and I just have the limit as x approaches 100 of the square root of x plus 10. At that point, plug it in. When I do, the square root of 100 would be 10, and I get 10 plus 10, final answer of 20. For number 9, our other algebraic limit, I give you the limit as x approaches 9, and yet again, you can't just plug it in, because if you tried, your denominator would be 9 minus 9, that would be a 0. Your numerator would be 1 over 9 minus 1 over 9, again, 0. So you'd say, well, this function does not exist at 9. That doesn't mean that there's not a limit as x approaches 9. If there's an algebraic solution, then there is going to be a limit. In order to get to that algebraic solution, I had to simplify the fraction within the fraction. I had to multiply by every denominator I saw in the numerator, which is an x and a 9. I said, well, that's better written as multiplying by 9x. I have to multiply by that 9x in the numerator and the denominator to multiply by an understood 1. When I distribute that 9x in the numerator, 9x times 1 over x is going to cancel out the x and leave me a 9. Into the second term, I would have minus 1 over 9 times 9x. The 1 over 9 and the 9 cancel, but I'm left with minus x. And again, please don't forget, you have to keep that limit as x approaches 9 until you can physically plug a 9 in, and we're not at that point. So now in my denominator, I had to put both factors down here. It had a factor of x minus 9 and a factor of 9x. In that numerator, I knew I needed to cancel out the factor of x minus 9 in the denominator. I knew that because that's what's causing the 0 in the denominator. I can't plug that 9 in there right now because that's going to cause the denominator to be 0. This one's not a problem. 9 times 9 is 81. I don't care about that factor. It's this one that's the problem. Now, be careful that you don't just carelessly say, oh, that cancels there. It does not cancel there. I have to have an x minus 9 as a factor in the numerator, but I can get to that if I factor a negative 1 out, and then I'll have x minus 9 left over. That's equal to what I had there. So that's what I did in the next step. I factored a negative 1 out of the numerator. Then my x minus 9's do cancel, and I'll have the limit as x approaches 9 of negative 1 over 9x. At that point, you can plug in the 9. Please keep in mind, that's why the limit does drop out in this step, because I physically plugged the 9 in. So I have negative 1 over 9 times 9, negative 1 over 81. Final answer. In my next one, you'll have a piecewise function, and you'll be asked to evaluate the piecewise function on the left side, the right side, and overall. We know the overall limit will fail to exist anytime the left and right give us different answers. If the left and right give us the same answer, then the overall limit is that same answer. In this case, as I approach 2 from the left, please remember with these left or right-hand limits, anytime you can plug the number in, you should. So am I worried about the fact that this is really 1.9 repeating here? Nah. I just plug a 2 into this top equation. I say for any number of x to the left of 2, the limiting value is going to be 3 times 2 plus 1. That's going to be valid for all values less than 2. Well, 3 times 2 plus 1 gives me a limiting value of 7. As x approaches 2 from the left on this function, the y value is approaching 7. Now, as x approaches 2 from the right, that's the second part of the function. It's valid for all x values greater than or equal to 2. So I would plug a 2 in for it, and the value that it's approaching is 4. Now, since the left and right-hand limits do not equal one another, the overall limit does not exist. Now, similar to that one, yet different, we have left and right-hand and overall limits in my next problem. So it's going to be beneficial in these problems if you go ahead and factor the numerator just to make sure that no factor of the numerator can cancel with a factor in the denominator. So I went ahead and I called my function f of x here, and I said, well, f of x is equal to factors of positive 4 that sum to get to negative 5. I said, well, that's negative 4 and negative 1. My numerator is going to factor to be x minus 4, x minus 1. Most importantly is what we need to see there is neither of those factors cancel with the x minus 3 in the denominator. Okay, now whenever I try to evaluate the limit as x approaches 3 from the right, just like the last problem, anywhere where I can plug it in, I should plug it in. So I didn't have to worry about this was 1.9 repeating. I didn't have to worry about this was 2 a bunch of zeros and then a 1 at some point. I was just able to plug in the number. Same thing in this problem. I can just plug the 3 in inside the numerator. 3 minus negative 4 is where that negative 1 came from. 3 minus 1 is where that 2 came from. I was able to just plug the 3 in the numerator. I can't in the denominator. It's going to cause a 0. So here's where I had to understand it's not technically 3. It's a number approaching 3 from the right. So my denominator becomes a number approaching 3 from the right minus 3 quantity squared. I'm supposed to keep in mind, well, that's going to be some infinitesimally small positive number there on the inside of that group. When you square an infinitesimally small positive number, it stays an infinitesimally small positive number. My numerator, after plugging 3 in for it, just gave me a -2. So here I had -2 divided by an infinitesimally small positive number. I need you to remember, anytime you have any finite number divided by a number approaching 0, you're going to get infinity. However, this is a negative over a positive, so you get negative infinity. Now, part B is essentially the same thing. You're just approaching 3 from the other side, and nothing's going to change. You still plug the 3 in to your numerator. When you do that, you get a -2. You'd plug the 3 to the left in the denominator. Now, technically, that's going to give you an infinitesimally small negative number inside of that group, but since you're squaring that, it doesn't matter that it's an infinitesimally small negative, because when you square a negative number, you're going to get a positive value. And ooh, I need to fix my answer there. I have a negative. So this is going to be an infinitesimally small positive value there. And that's why my answer is the same. I have an infinitesimally small a positive value dividing a finite number. Well, any finite number divided by an infinitesimally small number is infinity. This is a negative over a positive. I get negative infinity. Anytime the limit from the left and the limit from the right are the same, we know that the overall limit does exist, and it's the same as these two. So since these two are both negative infinity, that's why part C, also negative infinity. Now for number 12, we have the limit as x approaches 1 from the right of x plus 2 over the square root of x minus 1. Very similar to the last question. Anywhere where you can plug in the one-sided limit, you should. What I mean by that, if it's not causing the problem to be undefined, please just plug in a 1. That's what I did in the numerator. I have 1 plus 2. That's going to give me a 3 up there. No problem with that. In the denominator, I can't simply just plug in a 1 because that would give me the square root of 0, which is going to give me a 0 in the denominator, and I can't divide by 0. This function's undefined at 1, but the limit probably exists as I approach 1 from the right. In order to see that, I say, okay, I'm plugging in a number approaching 1 from the right inside of here. When I do that, 1 minus, or I should say 1 point, a bunch of zeros, and then a 1 minus 1 is going to give me an infinitesimally small positive value. It could be a trillion zeros and a 1 at some point. Well, the square root of an infinitesimally small positive value is still an infinitesimally small positive value. Any finite number divided by an infinitesimally small number is infinity. In this case, it's a positive over a positive, so I get positive infinity. For number 13 here. Now, please do remember, the only ones where you have to factor and solve algebraically are 8 and 9. So anytime you have the one-sided limits like 10, 11, and 12, you should just plug those values in. You plug in the full value wherever it's not making it undefined. You consider the one-sided limit wherever it would make it undefined. Now, anytime you have a limit as x approaches infinity, you could just memorize your rules, and you could say, well, John, in this one, anytime the degree of the numerator is greater than the denominator, you know your answer is going to be infinity. Yeah, you do. Anytime the degree of the numerator and denominator is the same, your answer is going to be at, I should have just circled these, your answer is going to be at the fraction of leading coefficients. Absolutely. In order to show where that comes from, you're always supposed to divide every term by the degree of the denominator in the problem. So in this first one, I had the limit as x approaches infinity. My rational function had a degree 3 in its denominator. So you see, that's why I divided every term in here by x to the third power. After that, I simplified. And keep in mind, we need to keep that limit until you can actually evaluate it as x approaches infinity. When I divided by x cubed, I had 5x plus 3 over x cubed. That term didn't simplify. Divided by 3 plus 5 over x minus 2 over x squared. Now, at this point in the problem, I knew that anything with an x remaining in its denominator, any finite number divided by a number going towards infinity, all of those are just going to become 0. So I said, well, I can go ahead and evaluate this limit. That's why the limit dropped from this step to this step. I plugged an infinity in for x. I had 5 times infinity divided by 3. Well, 5 times infinity is still infinity. Infinity divided by any finite number is infinity. We get infinity for our answer. For part B in this one, I divided by the degree of the denominator x squared. And when I did that in the problem, in the next step, the 8x over x squared just gave me an 8. Then I had plus 1 over x when I reduced down, minus 1 over x squared. This term gave me a 15 plus 4 over x minus 5 over x squared. Now, I knew every single one of these terms that had an x left in the denominator, all of those have to go to 0. That's what I did in the next step. So I take the limit as x approaches infinity. All of those that had the x in the denominator become 0. The only ones that didn't have the x in the denominator are your leading coefficients, the 8 and the 15, which of course that leads us to our final answer, 8 over 15. For the next one, this one's cool. It asks you to find all vertical and horizontal asymptotes. Now, for the horizontal asymptotes, I would rather you just think of it just as b here in this one. You can say, well, it's just the limit as x approaches infinity. Anytime the degree of the numerator and denominator is the same, your horizontal asymptote, so like in this problem, the horizontal asymptote would have also been at y equals the fraction of the leading coefficients, which would be your 8 over 15. We would have been able to answer that for this problem. Also, of course, the same thing as the limit as x approaches infinity. Well, the horizontal asymptote in this problem is going to be at the ratio of the leading coefficients, which is just going to be y equals 5 over 1. That's why I have horizontal asymptote is 5 here. Now, for the vertical asymptotes are going to exist at values that cause the denominator to equal 0 for any factors in the denominator that don't cancel with the numerator. If you have a factor in the denominator that ends up canceling with the numerator, that's not going to cause a vertical asymptote. It's just going to cause a hole in the graph. Excuse me. So in this one, I needed to try to fully factor my problem. In the numerator, this one was a little challenging to factor. I could easily see that all of the terms had a greatest common factor of x, so I went ahead and factored out that x. Then I had 5x squared plus 32x plus 12 left over. In the denominator, similarly, I had a greatest common factor of x squared. When I factor that out, I'm left with x plus 6. Now, I automatically know that this factor of x squared, it's not going to fully cancel with that x in the denominator, in the numerator. So I will have a vertical asymptote at 0. I already knew that in this step. The only question was, do I have a vertical asymptote at x equals negative 6? In order to know, I just needed to know, well, does this have a factor of x plus 6? You could have tried trial and error polynomial factorization. I showed my work over here thinking of it this way. I said, the only way that this is going to simplify is if x plus 6 will divide evenly into that factor in the numerator of 5x squared plus 32x plus 12. So that's what I tried here. And I said, well, x will go into 5x squared, 5x times, then 5x times x is 5x squared, 5x times 6 is 30x. We subtract that out. And whenever you do that, the 5x squareds cancel. 32x minus 30x is 2x. I brought down the plus 12. At that point, I had to say, well, how many times will x go into 2x? 2 times. So 2 times x is 2x. 2 times 6 is 12. This was gorgeous. This long division told me that, yeah, x plus 6, it is a factor of 5x squared plus 32x plus 12. And that tells me that x plus 6 times this is equal to that original trinomial. That's what I rewrote here. And then in this step, I showed that the x plus 6's cancel. The x cancels with one of the x squareds in the denominator, and I'm just left with 5x plus 2 over x. So this tells me that the only vertical asymptote, after you've fully simplified algebraically your fraction, which we have now, it can't factor or cancel anymore, the only factor remaining in the denominator that could equal 0 is an x. So you're going to have a vertical asymptote when x is 0, and that's going to be the only vertical asymptote. For the next problem, we had the limit as x approaches pi over 2 of 7 times the cosecant x minus 1 over cotangent squared x. And I could see a lot of students panicking when they look at a problem like this. You really shouldn't. I do want you to know your Pythagorean identities. Even if you only know this one, you can get by with it, even though this problem needs the cotangent squared identity, because all you have to do is work with the original one, knowing also your reciprocal identities. Like, for example, I know that cotangent squared is going to be cosine squared over sine squared. So all I have to do in order to get an equation that involves cotangent squared is to divide the original equation by sine squared. So notice, sine squared x over sine squared x is going to give me a 1. Cosine squared x over sine squared x is going to give me cotangent squared x. Divide the other side by sine squared as well. 1 over sine squared is cosecant squared. This gives me what I want. So I can say, well, okay, I can solve for cotangent squared now and say cotangent squared x is cosecant squared x minus 1. That's what I got here. Brought that into my problem. So this first step, I just rewrote cotangent squared x is cosecant squared x minus 1. And then I knew that, well, I cannot evaluate that at pi over 2 because at pi over 2, the sine is 1. The cosecant's the reciprocal of that. Well, the reciprocal of 1 is still 1. So 1 squared is also 1. Your denominator is just 1 minus 1, which is a factor of 0. So I can't just plug it in, and it's not approaching from the right or from the left where I could think about it just being a little bit bigger, a little bit less than that. You can't do that with overall limits. So I can say, well, okay, then I need to algebraically simplify. This is more like questions 8 and 9 where I have to algebraically simplify these and cancel out terms. That's what I'm going to do on this problem. I see that cosecant squared x minus 1 is a difference of 2 squares. It can factor by cosecant x minus 1 times cosecant x plus 1. The cosecant x minus 1 is the factor that cancels with the numerator, and that's beautiful because then I can evaluate my leftover part of the function. The limit as x approaches pi over 2 of 7 over cosecant x plus 1. Again, cosecant of pi over 2 is going to be 1. So from this step to this step, please notice I dropped the limit because I physically plugged pi over 2 into the place of x. I know that the cosine of pi over 2 is 1. 1 plus 1 gave me a 2. My final answer was just this 7 over 2. Gorgeous problem. Love that one. And then the last one, me trying to see if you get if you have an understanding of the intermediate value theorem. Remember, with the intermediate value theorem, it's just trying to get you to understand for a continuous function. If I want you to prove that a function is equal to any number, you just have to find an x value that gives you a y value lower than that number, find an x value that gives you a y value higher than that number, then you know that the x value that is a solution to the question has to be in between the two x values that you've selected. That's what I've tried to do here. So I'm supposed to try to show that f of x must be able to equal 4 for the function the square root of x plus the cube root of x. Okay, so I chose an x value of 4. The square root of 4 plus the cube root of 4. Now, cube root of 4 is an irrational number. It must have been 2 plus 1.587 rounded, because square root of 4 is 2. And then when I added that to this, my calculator said, well, f of 4 is going to be 3.587. Keep in mind, that is less than what I need. That's okay. Now, on the other side, I said, well, all right, why don't I try a 6? Now, in fact, when I was doing this problem, I tried a 5, but 5 was still less than, so it didn't help. I needed one y value lower, one y value higher. So f of 5 wasn't beneficial. I went on to f of 6. F of 6, the square root of 6 plus the cube root of 6, gave me a value of 4.267, which is greater than 4. So I know an x value that gives me a y value greater than 4. I know an x value that gives me a y value less than 4. That's all we need. So I can say, since f of 4 is less than 4 and f of 6 is greater than 4, we know there exists an x in between these values of 4 and 6, and the value of x that is a success, we say there exists an x equals c belonging to the set of x values between 4 and 6, such that f of c is equal to 4 by the intermediate value theorem. Now, this second part here, where I said let's use a graphing utility rounded to three decimal places to show where this f of x is equal to 4. So I entered y1. I had the function square root of x plus the cube root of x. y2 is equal to 4. I just graphed this out on Zoom 6, the standard Zoom screen, and my graph looked something like this. My square root function plus the cube root function came up like that. Y equals 4 came in through here. And in order to find the intersection, you just go second calc 5, hit enter 3 times, you get to that value.